All right, let's take a look at one more finite geometry. This one is a little more complicated, but still relatively small. And this one is called Young's geometry. Here's one set of postulates for this particular geometry. And by the way, it might be possible to set up other sets of postulates and end up with the same geometry. I think that's definitely true for this one here, but here's one set that works. Postulate 1, there exists at least one line. Postulate 2, every line of the geometry has exactly 3 points on it. Postulate 3, not all points of the geometry are on the same line. Postulate 4, for each 2 distinct points, there exists exactly one line containing both of them. And number 5, if a point does not lie on a given line, then there exists exactly one line on that point, let's say through that point, that does not intersect the given line. So postulate 5 is our standard Euclidean parallel postulate. Postulate 4 is our standard 2 points determine a line postulate. Postulate 3 just says not all the points are collinear. Postulate 1 is an existence postulate that allows us to start with a line. And then postulate 2 is telling us how many points are on each line. And this is postulate 2 is going to be what limits us to a finite geometry. So let's show that this is a consistent system, and to do that, we'll build a model that works. And we're going to formally prove our steps of our construction. And this time I'm going to use a format like this, where I have basically a paragraph style proof broken down into steps, and then a model showing what's going along with that at each step. So starting with postulate 1, there exists at least one line. We're going to call it L. So we'll model it like this. By postulate 2, every line of the geometry has exactly 3 points on it. Label the points, say A, B, and C. So line L is exactly the line containing A and B, the unique line, but it's also exactly the set containing the points A, B, and C. No more and no less than those 3 points because of postulate 2. Now postulate 3 says not all the points are on the same line, so there's another point, D, that's not on the line. Say put it down here. Now we have D, what do we have? So let's back up. Notice that we start with a line. Once we had a line, postulate 2 said we could get some points on it, specifically 3. Postulate 3 says now that we've got a line and some points, there has to be a point that's not on that line because all the points are not on the same line. So that puts us down here. Now, postulate 4 says, okay, we can take pairs of points, say D and A, D and B, D and C, and each one of those produces a line. Now, to intersecting lines, remember, have to intersect in exactly one point. We showed that if 2 points determine a line, that means that 2 lines can only intersect in at most 1 point. So that makes these different from the other original lines. So we've got now at least 4 different lines, 4 distinct lines. Now wait a minute, each line has 3 points, so there has to be a new point on each of these. Let's let those be E, F, and G so that line AD also contains E. The line that I've got demonstrated in red in the picture is exactly the set B, D, and F, and the set C, D, and G forms a line. Now, what about these points? Could they be the same as any of the original ones? Well, the answer is no. If you make, say, E the same as point A or point D, then we don't really have 3 points on that line. If E is the same as B or C, or F or G for that matter, then we're going to have two lines that intersect in more than 1 point, but different lines, and that's not allowed either. So these have to be 3 different points from what we had before. Okay, now the next thing is, what else do we have? Well, we got a parallel postulate. We haven't used it yet. If a point does not lie on a given line, there exists at least one line on that point, not at least one, exactly one, at least one and at most one line through that point. that does not intersect the given line. I almost did say line on that point. I will say through. Thus, there exists another line that goes through point D that doesn't touch the line containing the line which is the set ABC. Okay. Well, it's got to have 3 points on it, and we've already said they can't be the other 2 points can't be either points A, B, or C. And if they were to be either E, F, or G, we would have 2 lines intersecting in more than 1 point. So this gives us some new points. Okay, here's a picture down here. Say H and I. Now, let's see. So there's at least 9 points. Now, by postulate 4, there's got to be a line containing H and F. Okay, now let's think about this a minute. The line containing the line that is the set D, H, and I is the only line that's parallel to ABC through H. So any line going through H that's not this line has to intersect this line AB, the containing A, B, and C in at least 1 point. Okay, now let's look at H. We connect up to F. If we were to connect it up to B, we'd have the green line and this new line intersecting at 2 points. Not good. Okay, so if we go to H to F, it's got to intersect either back at C or A. Okay, I'm going to put it back to A. All right. Now, what about this? Now we have to do something similar with these other points. Okay, so let's make sure we've got all this. So AFH is parallel to line which is the set C, D, and G. So the orange and the maroon one do not intersect. There is no point right there. So these do not intersect. Okay. So any other line through H has to intersect the orange line. Okay. So there has to be a line that goes to B, from H to B. Okay. But it's got to intersect the orange line somewhere. It can't intersect it at C because that would touch this line twice. So it has, and it can't go through D. That would touch the purple line twice. So it has to go H to G to B. That's the pink line here. All right. Now let's see what else we got. In a similar manner to what we just did, we've got to have a line from H going to C. So you have a line from H to A, and it goes through here. We also have a line from H to C that's going to include E. Okay. If we had one going from H to C and it didn't include E, we would have more than one parallel there. So there's a line going that way. I illustrated that one with an arc here. So the blue arc. Now, what about I? I's out here by itself. Well, I has to connect up to every one of these points, right? Because any 2 points determine a line. Now, remember, we already have a line through I that's parallel to the dark blue one up here at the top. So any line through I is going to have to also go through, it contain exactly one of A, B, or C. So if you go through, let's say go to A first, from I to A, there's going to be a line there. what else does it have to, it's going to have to intersect some of these other things here, okay? So why does it have to intersect the orange line? Let me back up just a minute. So we're going to claim that the 4 lines that we've already got through H are the only lines containing H. Okay. So far, what we've had is consistent with postulate 4. So remember that BGH, the pink one here, is parallel to AED. So any line through H, this is the one and only parallel to this red line. So any line through H has to go to include A, E, or D. Okay, and we already have line here, this one that contains A. So there can't be another one through H and A. There can't be another one through E and H because we got that, and there can't be another one through H and D. So that's all the lines that we have. Okay, and we're going to use a similar argument down below. So let's take a look at let's look at I. Okay, well we've got a line going through I to A. Okay, why does it have to do that? Well, it has to go through there because if not, well, there has to be some line going from I to A. That's 2 points determine a line. Now, what I claim is it has to have point G on it. It's got to have a third point. Why does it have to intersect here? Well, this line cannot contain B or C because that line would intersect this line up here twice. Similarly, it cannot contain E or D for the same reason, and it can't contain F or G for the same reason. Okay? Well, what if it's some other point? Why couldn't it be something different than G? Well, if it was something different than G altogether, then we would have, then this line here would be parallel to the orange line. And we already have one parallel. Let's see, do we already have one? No, we don't have another one parallel to that yet. Okay, I think what I want to do is the next thing is actually what I've said here. I want to show that there can't be another point. Okay, suppose there is there are 9 points here. Suppose there was a 10th point, X. Okay, what would happen then? There'd have to be a line through H and X. But this is going to contradict what we've already said. There are no more lines through H. And so that means there can't be more than this 9 points. So this is sort of why this is collapsed back. So then now when we get to this line here between I and A, it's got to have a third point. Well, it can't. What could it be or what could it not be? Well, every one of these, there's already every other point is used on a line with A. So that forces the only one left to be point G. Okay. Well, what about what else can we have? So we got to have a line I and it's got to contain I and F. Well, it's got to contain a point up here. It's got to contain either A, B, or C because we already have the only parallel to that line, A, B, and C. Can't be B because then we contain F and B. That's 2 points on the lines intersecting in 2 places. It can't be A because of then it would contain A and F. This line here would contain 2 points in common with this new line. So the only place it could be would be to contain C, which I want to make by a big arc like this. And then we can do a similar thing. There has to be a line containing B, E, and I. So I has to also go through B, okay, but where else could it go through? Well, it's got to go, there has to be a line containing I and B. Well, it has to go through E. If it were to go through F, we already have a line through B and F. If it were to go through G, we have a line there. C, we already have a line there. B and H has a line there. B and D. The only one left could be E to connect it up. So we get a line there. And a very similar argument then says we have to have one connecting E and F, and it's going to actually go through G as well. And I think that gets everything that we have. So we've looked at all the different pairs of points here. They generate exactly one line each. Each pair, that's the 2 points determine a line. And we have this. There's 36 pair of points, which give us at most 36 lines. However, each line contains 3 points. So the actual line has been counted 3 times, so there are actually 12 distinct lines. And we actually already have all 12 lines there. So here's our model, or here's our illustration of the model. And the coloring helps if you can see the coloring. But this red one here is the points A, E, and D only. This aqua one here is a line. So I've used line segments when I could, and then used 3 of the lines are done with arcs of circles. So here's one here that contains C, I, and F. E, H, and C are on one line, and I, B, and E are on one line. And so here is our actual model. Our model has 9 points, A, B, C, D, E, F, G, H, and I. And it turns out that there are 12 lines, and 2 lines are parallel to every line that we have. So I've organized the lines, the 12 lines in this table, and every line of the table, each line is parallel. And I've just listed the 3 points, but the 3 points are actually the lines. So actually the lines really, these should be sets like this. This is actually a line. Okay, and here's another line. And notice that if we take any 2 across this first row and do an intersection, we're going to get the empty set. So there's a set of 3 lines that are parallel to each other. Okay, and the same thing's true for the second line. And notice that each line here contains all 12 points. Each line in our table contains all 12 points. Okay, and the color coding here matches the diagram above. Can help us to keep this straight. And let me add these things here, so because these, of course, these lines are sets of points. And notice that it satisfies all of the properties, right? Through any point that's not on a line, there is exactly one line parallel to the given line that goes through that point. And let's see, any 2 points are on exactly one line. And there's exactly 3 points per line. And let's see, there's at least one line. So I think that was all of the postulates. Let's see. And not all the points of the geometry are on the same line. We actually used that right at the beginning here to get a point that was not on the original line. Okay. So here, let's see, what do we know? Well, those were the postulates. There exists at least one line. Not every line of the geometry has, or every line of the geometry does have exactly 3 points on it. Not all the points of the geometry are on the same line. For each two distinct points, there exists exactly one line on both of them. And if a point does not lie on a line, there exists exactly one line through that point that does not intersect the given line. So that we made sure that was that worked. Some propositions that we've proved on the way. There exist exactly 9 points and 12 lines, no more or less on this one. There exist exactly 2 lines parallel to any given line, and these 2 lines are parallel to each other. We have there exist exactly 4 lines through each point, and intersecting lines intersect in exactly 1 point. And you might notice that this actually satisfies all the properties of an affine plane geometry. There exist at least 3 non-collinear points. That's certainly true. Every line contains at least 2 points, specifically 3 in our case. Given any 2 distinct points, there exists exactly 1 line containing both points. True. And the parallel postulate, given a line and a point not on it, there exists exactly 1 line containing the point that does not intersect the given line. That's true as well. So this actually is an affine plane geometry with 9 points, 12 lines, and 3 points per line. So that's a little more complicated one there to build up than we looked at earlier. We've come quite a ways from our 1-point geometry now. But that gives you a good way to look at how some of these postulates interplay with each other. And in this particular case, we were able to limit the size of the geometry to be finite, really because of a couple of things in the interplay. First of all, that there were only 3 points per line, and then the fact that there was a unique parallel. And so that limited the size of the geometry. Okay, just to wrap things up for this playlist, it's time to go read some stuff in the textbook if you're in my class. So our textbook is College Geometry, A Unified Development by David C. Kay. The sections I would like you to read now are sections 1.1, 1.2, and 1.3. That's pages 1 through 18 of the text. And then Appendix C and Appendix F in the back of the book as well. And this covers material very similar to the way that we've covered some of the stuff in our first and second playlists on YouTube and our first and second set of notes for my class. So hopefully you're ready to do some homework on this now and ready to dive in and experiment with these things, maybe look at some other finite geometries, maybe prove some more propositions. Enjoy.